So another way to think about what dimensions tell us, what they mean, is to look at a whole bunch of different objects of different dimensions. So that's what we'll do in this video. It'll be a tour through the dimensions. And we'll start with small dimensions and then move up. So d equals 0. Those are points. So these points have 0 width this way or this way. They're just infinitely small points. And a collection of these would still have a dimension of 0. So points are 0-dimensional. Next, let's look at the Cantor set. This is the middle thirds Cantor set. We've looked at this before. So we are always removing the middle third from these line segments. And we end up with this shape down here, and it will continue on. And these lines are drawn with some thickness, but they shouldn't be. These are really just points. But if they didn't have a thickness, they wouldn't show up on the piece of paper. So as we iterate this procedure, we get just dots. And so we might think, well, this is made up of dots, points. It should have 0 dimensions. But as we've seen, it actually has a dimension of around 0.63. So it's between 1 and 2 dimensions. It starts off as a line. It ends up as an infinite number of points. So it's somewhere between 1 and 2 dimensions. A variation on that is the middle fifths Cantor set. So here we remove not the middle third, but the middle fifth. And I think this was a problem for homework or maybe even a test. And you should find that the dimension here is given by 0.756. So this dimension is higher than that for the middle thirds Cantor set. And maybe that makes sense. You can kind of see that. This is linear, right? Lines are one dimension. This is a little more line-like and a little bit less point-like. So two different Cantor sets with different dimensions. Next in our tour, well, we would have just a line. So that could be a curved line, straight line, jagged line. Lines of any size, any finite size, will have a dimension of 1. So lines are one-dimensional. And as we move up in dimensions, the next fractal I want to show you is something that we haven't encountered in this course, but you will have seen if you took the other Complexity Explorer MOOC that I took on dynamical systems. So this is the Annalen Attractor. It arises from a discrete dynamical system. And it's a little bit hard to see, but this is a sort of boomerang or U shape, and it's bent over on itself so that anytime you zoom in on a line, it actually turns out that it's 2 lines. So this looks like a long collection of lines, but the lines are infinite and bend over themselves in a complicated way, and we end up with a dimension of 1.26. So this is between 1 and 2 dimensions. Next is a fractal that's very, very familiar, the Koch curve. And as we've seen, this has a dimension of log 4 over log 3. We saw that from self-similarity. There are 1, 2, 3, 4 pieces, each of which is self-similar to the large piece. And the scaling factor is 3. This has to get stretched by a factor of 3 in order for the small one to be as big as a large one. So there's some 4 against 3 relationship that happens again and again. But there are other fractals that have this dimension. Here's one of them. This is a 2-dimensional version of the Cantor set. So we start with a square, and we cut out a cross from that square. Then we would have 4 squares. We would cut out a cross from each of those. Then 16 squares, cut out a cross from each of those, and so on. So again, we have a 4 against 3 sort of thing going on. There are 1, 2, 3, 4 small shapes, and this one I would have to stretch by a factor of 2, 3 in order to be as large as the full one. So these two shapes have the same dimension. And this illustrates nicely, I think, that dimension doesn't tell you everything about a shape. I would say, just qualitatively, to me these two shapes feel really different. This is some sort of weird dust tile sort of thing, and this is something that looks a little bit like a coastline. but nevertheless their dimension is the same. And that means they scale in the same way, thinking in terms of what happens if you double or triple them, or how many boxes you would need to cover them. And here's one more fractal that has that same dimension. This is a branch tree structure for an L system, and this turns out also to have a dimension of 1.262. So what this means is that all of these shapes scale the same way. Their properties change in the same way as you scale them up or down, as you zoom in and out, but they certainly look different. So dimension isn't everything. All right, so that's 1.26, somewhere between 1 and 2 dimensions. Let's keep going. Here is a variant on the Koch curve. Got a little bit truncated here, sorry about that. This is one I think we've experimented with before, and this has a dimension of log 5 over log 3. So does this Fractal Snowflake. That was one of our early examples. Here's a shape. There's 1, 2, 3, 4, 5 of them. The stretch factor is 3. So again, two rather different looking fractals. They have the same dimension. That means they scale similarly, but that doesn't mean that they were formed in the same way or that they look the same. All right, continuing to a slightly higher dimension. This is a variant on the quadratic Koch curve again. This is one also we've explored before, and this is kind of fun because its dimension turns out to be exactly 1.5. So in a sense, this is right between a one-dimensional line and a two-dimensional surface. All right, next up in our tour is the Coast of Norway. So some researchers did box counting or something like this to estimate the dimension of the Coast of Norway, and they got about 1.52. I'm always suspicious of the last digit here. I think it's really hard to estimate dimensions, but I haven't read the paper, so I don't know. Maybe they really were able to get this degree of accuracy. So this type of Koch curve has a dimension of 1.5. It's a certain amount of crinkliness that leads to that being between 1 and 2. And it turns out that the Coast of Norway is also about 1.5. So in some sense, maybe it has a similar amount of crinkliness. It scales in the same way. Next up, our friend the Sierpinski Triangle. This is one of the, again, sort of standard fractals. This would be log 3 over log 2. Again, something that we've worked with before. Here's a variant on the Sierpinski Triangle. So now instead of 1, 2 along the bottom, they're 1, 2, 3. So the stretch factor is 3. And this dimension is higher than that. And again, I think that sort of makes sense because, at least to me, this looks a little more like a surface. It's a little more filled in, whereas this is a little more sparse, has lots of bigger holes in it, more holes in it. So two Sierpinski triangles with slightly different dimensions. Let's see. Next is diffusion limited aggregate, a DLA fractal. These long interactive dendrites, I like them. I always find the asymmetry of this refreshing after looking at all of these that always look a little too perfect to me. So a DLA fractal has a dimension of around 1.70. Again, I might be suspicious of that. And so far as I know, the only way to calculate this is with box counting. So this is a numerical result, not a pencil and paper or analytic finding. Here's another Koch curve variant. Now the angle is very steep, and this is getting really close to 2 dimensions now, and you can kind of see that, right? There's a lot more ink here. It's a lot more filled in. Next, we have the Sierpinski carpet. We're getting closer to 2 dimensions. Again, this is looking more and more solid. It's still a gasket. It has holes in it at every scale, but it's a little more solid, a little bit heftier. All right. So here's one that I think is fun. This is the Sierpinski Tetrahedron, and it's a little bit hard to see in this sort of black and white thing. You might be a little easier to look at online. But the picture here is that there's 1, 2, 3, 4 of these pyramids in the large pyramid. So that would give us, if we did self-similarity, log 4 over 2, which turns out to be 2. So this is a 3-dimensional shape. This is supposed to extend up, but it turns out to be exactly 2-dimensional. So in a sense, it's all area as we keep going. All right. Next up, broccoli. This was also done by some 3-dimensional version of box counting. The estimate I saw was 2.66. I'm very suspicious of that number. But again, this is something that's between 2 and 3 dimensions. So 3 dimensions would be a volume, a cube, a sphere, something that fills up space. 2 dimensions is a surface, and this has branches, and then branches and branches, and so is somewhere between 2 and 3, but closer to 3 than to 2. All right, a few more natural examples. Surface of a brain. This is a human brain. Apparently that's about 2.79. So this surface, again, you'd think it's 2 dimensions, but it's crinkly, it's bumpy enough that it bumps up and is almost actually 3-dimensional. Just like those Koch curves, you'll think they should be 1-dimensional, but they're bumpy enough that they start pushing up into the 2nd dimension. And lastly, another physiological one, the surface of a lung is almost 3-dimensional. Again, I'm suspicious of that digit because I just think it's hard to do box counting that accurately. So a lung is takes up space inside of your chest, but the surface is so folded and divided and branched that it actually pushes up, and the surface, instead of being 2-dimensional like most surfaces are, is actually really close to 3 dimensions. So, so this is a tour of some structures with different dimensions, and of course there are thousands of other structures that one could look at, but maybe stepping back and just looking at these shapes gives a little better sense of what all these dimensions mean.